So we're going to start talking about program analysis, and in particular, program analysis, of course, to find vulnerabilities. And as you know very well, there are different approaches to finding vulnerabilities. Some can be, manual, involving just a human. You guys are too young. Who knows who this guy is? God, you're so young. Who is this? Maybe you know him better as this guy for semi-automated. Yeah, that's the original RoboCop, And then we have fully automated, also from the original RoboCop. It was the actual, sort of arch enemy of RoboCop. Different approaches. The manual vulnerability analysis obviously has, it's very simple. It's fundamentally taking fish, putting him in front of a program and say, where is the bug? Fish will say, this is the bug in record time. The problem is that we cannot clone fish yet. And so there are not a lot of these kind of experts that can just, auto-magically find vulnerability in such a short time. So that's a problem. But this type of analysis, being manual, allows humans to actually reason about the program and finding logic flaws that are difficult to find in an automated fashion. So it has advantages, and that's why nowadays, we use humans all the time, okay? But it doesn't scale. So one way to help is to have human and machine work together. So we call tool-assisted vulnerability analysis, where you actually have a tool, and we will see some, that at least can point you in the right direction. It's great if somebody say, oh, this is a gigantic binary. I think 90% probability the vulnerability is right in this routine. It's like, that's already awesome. Maybe I don't have the exact vulnerability, but instead of analyzing megabytes of code, I can focus on a specific area of interest. But you still need a human, so you can go faster, and but you cannot scale by just turning on your cloud account to 11 and see things happen automatically. So, and then you have the holy grail, in a way, of what we do, that, we want to, something that points at a binary or a website and say, okay, these are the vulnerability, this is the exploit, and maybe even this is the patch that will take away the vulnerability, and so on. And of course, as we have seen, this requires that you have a model that is able really to represent what you're looking for. And this is not very easy to do in a general way for certain kind of vulnerability. And of course, can only detect the vulnerabilities that you have modeled. If you don't have a model, you don't see it. The main advantage is it can scale. And that's why there was an enormous interest in this type of completely automated capability of finding vulnerabilities and maybe even exploiting them, because then your only limit is computation. And then, as we know, we have the cloud, so we can really increase our computational power. And so we can do a lot more. It is also true that some of these automated techniques don't scale in certain cases. There are causes. There are in certain situations, certain analysis technique can actually explode in complexity and become intractable. And of course, there is the problem with halting. So the halting problem tells us we cannot create a program that tells us if a program halts. And so by the same reason, we cannot say if a program has a vulnerability or not in the general case. And of course, we have these vulnerability analysis systems. You can buy them. They're actually things that you can buy that find vulnerabilities. They usually rely on a composition of static and dynamic analysis technique, and we will see what they are. And fundamentally, they try to understand how data that is under the control of the attacker enter the system, how it's manipulated, and what are the bad things that can happen that will disrupt the security of the application that is unsafe condition. And of course, this vulnerability analysis, for example, in the case of binary program, the main goal is to generate crashes. So to have something that say, hey, there was an illegal access or something bad happened, and therefore this is worth exploring more. And different techniques have different advantages and disadvantages. One is the replayability of an analysis. So when an analysis gives you a result, will you be able to create an instance of the problem that the technique found? Okay, so the ability to actually have the input that will create the vulnerability. What if I tell you, oh, that could be a problem? I say, yeah, okay, but how do I get there? What is an input that would cause this? There is low replayability. Another interesting way to look at these techniques is the semantic insights. So understanding exactly what is the role of certain input in order to cause a certain condition to happen. For example, understanding, oh, is this part of my input that is used in a conditional, in a path that led me to this part of the application where the problem was. That can be very useful because, for example, once you have identified that that's the part of the input responsible for that branch, say, oh, what if I take a different value for that particular thing? And you can explore different branches to find more vulnerabilities. Sometimes you can get no semantic insight. So say, well, I got this input, got a crash, that's it. That's all you get. Yes?
Why wouldn't most tools have a semantic insight? Like even GDB, you can tell what kind of input.
It's always a trade-off. And we will see some examples of analysis that will give you some powerful concept on one end, but that is paid in terms of, for example, low replayability. But they give you more semantic insight. And so the trade-off is always, I want everything. Of course, I want great replayability, semantic insight, scalability. But those things, unfortunately, you don't get them. It's all about trade-offs. High replayability, for example, usually imply low coverage. Low coverage means that you don't see a lot of the application. But what you see is very real. It's very replayable. Dynamic analysis is a typical concept of that.
Log every input?
You can. And actually, you will see there are techniques that exactly do that, log every input. But still, if suppose that, we will get when we talk about dynamic analysis. But the basic concept, if you have something that actually execute the program, and you don't know, when you execute a program, you execute a very small subsection of the code because there are certain things that are never covered. So for what has been exercised, you have some insight of what the program does. The rest, well, you don't know. And so there is low coverage of what the problems could be. If you have low replayability, oftentimes you have a lot of false positives. That means that there are many situations where you say, oh, there could be definitely something bad there, but actually there's none, which means that you waste a lot of time, and if you waste too much time, you will stop using it. Semantic insight usually, for example, implies a lot of overhead because you have to instrument the application at different points in order to understand what is the relationship between the behavior of the application and the inputs that it receives. And of course, if you have replayability and semantic insight, usually you have some sort of lack of soundness. And we will see what that means. And this means that you will get false negatives. That means that you will miss something. So now the state of the art of war, so the state of vulnerability analysis, and especially with binary, is pretty bleak. There are a bunch of tools. There are closed source commercial tools that do a good job. Oftentimes you can have, especially in research, you find a lot of tools that have been published. They do all these different analysis techniques, but they're not available. And others that are supposed to be open source but are effectively closed source, meaning that you will find on a website some super old version of some university prototype that is non-maintained and it's fundamentally unusable and for which you will have no support. And I'm saying this because we will talk about Anger, which is something that we developed in our group that was really trying to solve this issue by providing a framework that is open source and over which you can build your research. And if there is one thing, if you learn a tool, now you know how to use GDB and Radar and LibNet and libpickup. Anger is another very important tool if you want to go down the path of binary analysis, and other forms of analysis is very good. But going back to finding vulnerabilities, with vulnerability analysis, automated vulnerability analysis, we try to find an algorithm that is able to get source code or binary and identify flaws. Okay? So in a way, we want to replicate whatever is going in the mind of a human in terms of how they find flaw. And there are two ways to do it. As we mentioned, static analysis. And the advantage of static analysis, which is sort of like an abstract interpretation of the code, is that you can, most of the time, reason about all the behaviors that you observe. So you can make statement like, oh, this program will never reach this particular condition, or will never reach this particular state. And in dynamic analysis, instead, you have some form of execution of the code. So you see in practice how the state of a program evolves. But of course, you have limitations. You only see what is actually executed. And so these two have, different advantages and disadvantages. So especially in static analysis, the basic idea is to create some kind of model of the program, because if you just execute the program, you effectively doing dynamic analysis, and you want to analyze all possible inputs without running the code. So I want to say, even if this particular program receives any input for this particular variable, I know and I can prove that this piece of code will never be executed, or that this data will never flow to this location. There is no way. You can actually build algorithms that in specific conditions will prove that that is not going to happen. And the cool thing is that you can find possible bugs, but in addition, you can also prove the absence of certain condition, which is very powerful. If I can say, I can prove that this is never going to happen. And this is something, a form of verification that is used a lot in avionics and in other, mission critical components, where you want to say, maybe, there can be other type of problems, but I never prove me that there was never an interleave of actions so that when the pilot pulled this thing, the flaps are not moving, or something like that. So static analysis has been part of sort of like computer science for the longest time. Is using compilers to, for example, optimize code, and for, performs all sorts of analysis to find problem. And also, of course, informal verification, where you want to prove some property. One of the challenges with static analysis is the concept of soundness, precision, and most of all, scalability. So soundness and completeness sometimes is misunderstood. The basic idea is that you have a program, P, and imagine these are all the possible behaviors of this program. Okay, so this is all the things that a program can do. And then in static analysis, you build an abstract model of this program. And, if you want to be sound, you over-approximate all the possible things. That means that your model, in theory, can do a lot more than what the program could be. But it has everything that your program could be. So it's an abstract version that maybe instead of, in that particular domain, is simplified or generalized, and you decide, this is my over-approximation. And you can see already here the problem. If you over-approximate your sound, okay, so you know that you will find all the problems because you're covering all the behavior, but you can say, oh, there is a problem here. And that's not something that a program can really do, and as a result, you have a false positive. Of course, you can limit that by improving the precision of your over approximation. So with the idea that you try to get as close as possible at the actual program behavior. And then you can have completeness. Completeness, a program or an analysis is complete when under approximate the behavior of a program, but all the behaviors are contained within the behavior of the program. So completeness is cool because if you find a problem, you know there is a problem. But you cannot never know if you found all the problems, because there could be a problem here that your complete yet unsound analysis wasn't able to discover. So you can see a completeness or soundness. An example that I like that I read somewhere is like a jury. So a sound jury will send all the criminals to jail, but they're gonna make a mistake and send innocent people to jail. A complete jury will always send guilty people to jail, but a lot of guilty people will go free. So you have your false negatives. So your trade-off. And most practical approaches that use a large scale are neither. No, they're not sound and they're not even complete. So they have false positives and false negatives. But you can decide in your research to pursue one respect to the other, depending on what you want to do. So sound approach can prove everything, okay? But the results need to be verified because you have false positive. And complete approach always produce a result that is correct. If they find a vulnerability, you got that vulnerability. But you cannot be sure of the absence of the behavior, which is sometimes very important. These are examples of analysis. You can have control flow analysis, so you understand how flow transfer. You do control flow analysis when you look at the CFG, the control flow graph, or your binary program. And this is sort of deceivingly complicated or deceivingly simple, depending on how you look at it, meaning that understanding how flow can move in an application, well, if you have absolute jumps and call to absolute value is easy. But imagine when you start talking about indirect call, so where you jump at the content of a register, or you have switches, or you have jump tables, or the different data structure, then understanding just the problem of understanding where a function starts and ends, and where all the possible control flow can happen, for example, to enforce control flow integrity, as we have seen, it's actually difficult. Data flow analysis, also very common. You reason about how data can flow through your program. Data dependency analysis, where you understand how data is defined in terms of other data. Points to analysis, classic pointer analysis in order to determine which pointer point to which parts of memory. Even alias analysis is very hard. Understanding these two pointers at a point in the execution of the program. Could they ever point to the same value? And that's something that is very difficult to do. In fact, Ben Hardikoff in our department has been working on that stuff and has come out with super advanced technique. Another thing about it is value set analysis. For example, instead of generalizing a range to from 0 to 1,000, maybe you can decide, oh, this can only happen at because of the type of data structure in certain specific forms, and so you can have a better description of the values that can be taken by a program. So imagine using static analysis to detect vulnerabilities. Your first super good static analysis tool is called grep. You take a program and say, oh, if there's string copy, that's a buffer overflow. My model is if I copy stuff using string copy, there could be a buffer overflow. So I flag all string copy as a vulnerability. So in my model of that vulnerability, I will catch all the vulnerability, right? The vulnerabilities will all be identified, but of course, you're going to have a lot of false positive because not all string copies are bad. This in particular is obviously bad, as you probably immediately recognized. But of course, you can refine your model and say, okay, let's just go. String copy may be a little brutal. What if I have a model for the size of the source and destination? I model the semantics of string copy and maybe other functions like memcopy or other forms or scanf and so forth. And then I have some safety condition that say I want the length of, in this case, this argv1 be less than the length of buffer. And if there are some situation in which this cannot be satisfied, then obviously I have a vulnerability. Do I know, for example, how do I exploit the vulnerability? No, but I know that there is a potential vulnerability there, and so more precisely, I can point at a human analyst, hey, look at that. That is looking pretty bad. And then there is another part of the program where it's obvious that the length of the stuff that you copy in will always be less than the size of the buffer. And in that case, you can rule out, because you have a better model, you can rule out the fact that there is a vulnerability there. Of course, not everything is super simple. For example, you can have a program like that where, for example, you do reference a buffer using a value that first you got from some function, and then there is some weird condition, and only in the condition you shift that buffer. And then, so when I do this, is it safe? Okay. Depends, of course, do you have a model for this? Because if I have a model for this, and I know, for example, I can extract the range that will be returned for that index, then I can determine, oh, this, whatever is the max, whenever is, shift this way, will be more than 256, and that's where you can decide or not. Sometimes modeling this, if this, for example, is an input from the user, forget it. You cannot guarantee that particular condition, okay? And so you can be conservative, and assume that IDX is always unsafe, or, you can find better model that are more sensitive to sensitive meaning more pay attention to many different things, and are able to give you a better answer or a more precise answer. And in general, sensitivity, okay, is a really important problem. Actually, I mean, somebody here who's worked on sensitivity in, not because he's a sensible guy, but because he's, or a sensitive guy, but because sensitivity can increase precision. So fundamentally, you don't take into account certain things, but you take into account the things that allow you to disambiguate things that could be confused together. So, of course, the problem is that the moment that you disambiguate stuff, you augment exponentially the number of states or the number of situations that you have to analyze. And this, of course, can create problems. So, for example, in flow-sensitive analysis, you can, take into account the flow of the operation when you make a decision in a specific location. In path-sensitive analysis, you keep track of what conditions have been taken when we have reached a certain point in the program in order to determine if that program was correct or not. Or in context-sensitive analysis, when you have a call, you might decide that not all the calling the same place is not the same if it's called from very different locations. Yes?
So when you're writing a program, is there an easy way that you can make it, more subject to these analysis tools?
Very good question, and the answer is absolutely yes. And in fact, many of the techniques for static analysis are actually helped by something called annotations. So the human can help the analysis system, especially for those tasks that are difficult. For example, there is a system call. And the system call is called, you receive back something. What is the relationship with that system call and your program? It's very difficult. For example, imagine a classic example that we always refer, you want to take an ASCII string and return an integer, okay, A to I. That, to model to model the internals of all the loops that go through the string and take the A and then decide it and comes out with a number, for a human being, it's pretty easy to understand what is the side effect of that. A string has been consumed, an integer has been produced, and you can even create some association between the two. So I could decide, hey, I don't want my analysis to go deep into A to I to finding out what's going on. I'm going to tell you. This is a function that takes a string, returns an integer, and the two are related by this particular relationship. Somebody calls them a function summary. It's a way to represent the relationship between input and output. So when the analysis gets there, instead of entering the function and maybe exploding in the complexity of that function, you can say, oh, somebody told me that it's just this. Oh, I'm going to go forward and improve the scalability of the thing. And just to give an example of context sensitivity, imagine this program, and you can see that there are some functions that take a certain type and then call another function that takes the parameter and invokes sort of like a method. And you can see that here you can have T, or you can have a subclass of T that has for the method H a different implementation. For example, this is download some code from the address Z, while instead H, if the type is T, is to send some data to this location. So you can imagine different locations and different situations in which you say, okay, if the call comes in this direction, I know, thanks to my analysis, that the type of X is T, and Y is the user IMA, which is your cell phone identification number, which could be a privacy leak if it's sent to somebody that you don't want to, and destination is ok.com something. If the call to this function comes from here, I know that Y is nothing, but the website could be something evil, like evil.com. If it comes from this site here, I know that the Y will be SMS messages, but it would go to google.com, and that would be fine. So now, if I do not have context sensitivity, fundamentally, I have to take the union of all these different things, and my model say, at this point in the program, X can be T or U. So I imagine that this is actually when X is U, of type U instead of type T, which is a subtype. And so Y can be fundamentally anything. Could be nothing, something that is private to the user, or some SMS message. While the destination could be ok.com, evil.com, and google.com. So because these are all the values that I see coming to this location from all these different calling contexts. So when I do my analysis, I say, oh, is there a vulnerability? Oh, yeah, because here I can see, U is one of the possible types. So let's see, I could download code from any of this site, whatever Z is. So I could download code from evil.com and be completely vulnerable. So I would flag this as a vulnerability. Of course, here, same thing. This sends data, so I could send the IMA or IMEI, the SMS to any of the website. And sending this, my private information to evil.com is probably not a good outcome. So people could say, oh, consider this data flow and the way in which you can reach that, there is a vulnerability there. I'm leaking private information. So not good. Or you could be context sensitive. So in here, when you have this call, you know that you came here with the context I've been called F1 that, which called G, which is unique to this path. So now I know two things. A, that the type is only T. I don't have to do the union of the U and T instances. I know the type of T. So I know that when I dispatch I usually probably should be X, H. When I dispatch that method call, I know that it is going to use the T implementation of the method and not this. So I know that we'll send data, my user IMA, to OK.com, which is fine, which is the intended value. Okay? And I can go on and say in the second case, I also have a different context, so I can differentiate between these two cases. The type is T, and so I know now that since the type is T, I'm going to use this, and I'm going to send nothing to evil.com. And therefore, I know that this situation is safe. And once again, if I do the third time, in the third case where I have this context, first F3 that calls G, then I have type U. So I know that when this method is dispatched, it's going to go to the U implementation of H, and I will download code from google.com. And at this point, 3 vulnerabilities that were possible there became no vulnerability because I added that level of sensitivity. Yes?
So is there a way you can add, instead of adding that as like an annotation, add that to the code itself so that you can guarantee in the code it never reaches those other states?
You can. So of course, if you think about it, this becomes sort of almost a sanitization problem. You can say, hey, when you write the code, the right way is to think, how can this data flow? And you can put in the code assertion or checks that say, this will never happen. So that's how you can add additional checks to prevent this from happening. Yes, absolutely.
This is called contract programming, and it's widely used.
Mm-hmm.
It's been widely used in recent days. So.
Yeah. I mean, in general, if you look especially for security critical software, there is a lot more that goes in addition to the code. You have contracts, you have assertions, you have hints, the compiler, even things that might suggest simply that you cannot optimize away certain code. You know, one problem is, for example, there could be, imagine some code that is cleaning up, zeroing an area in memory after a secret key has been stored there, and you want to say, hey, do not, since the compiler say, oh, you're writing zero this, but then you never use this memory. So okay, so if I don't do it, you never use the memory, nothing bad is going to happen. But now, you could do another allocation, and you happen to be able to get that memory. So you might want, for example, to provide hints to the compiler, saying, do not remove this part or optimize it away.
Would it be easier to just tell the compiler not to optimize anything?
Well, then you have shitty code, which is not necessarily a good thing. And so yeah, you can of course optimize nothing, and then you have really slow code. The good trade-off is having optimization and good code. Static taint analysis. This is taint analysis, and we talked about it. It's fundamentally a data flow problem where you represent how data flows through to the program, and it was introduced actually from the guy who did Perl, who actually decided that he wanted to prevent exactly the common injection attacks that we have seen in scripting languages. And so it introduced into Perl the ability to track how data flow, how data moved through the program, and could identify exactly situation in which this was not safe. So if you imagine here in C, you would fundamentally specify which part of the program are a source of tainted data. And for example, in this case, these are sort of annotation that help the compiler say Well, in main, your argv is actually tainted because comes from the user, could contain anything, so it's bad. Okay, and I want to do a printf in which the format is untainted. So if I see a data flow where something tainted becomes something that should be untainted, okay, then you know that there is a possible flaw. In this case, a format string vulnerability attack. And so it's fundamentally understanding what we call the possible path from sources to sinks. And these are examples of static analysis. Then we have dynamic analysis, which are sort of the dual. Instead of having a model that allows us to represent all the behaviors regardless of the input to the application, we have something that in some way has a specific input to application and just execute the program itself. And this is super powerful in terms of reliability because you know exactly what input will cause the specific result, but of course there are coverage problems. So if we go back to the same problem, taint analysis, you can do that with dynamic analysis as well. You just instrument your program, and every time you have something that is defined in terms of something else, you say, oh, now this piece of data is also tainted. So fundamentally, you model how the taint is introduced, how it's propagated, and what also represents untainting, because you have to model the fact that some tainted data can become untainted because, for example, you sanitize and you sanitize it correctly. And once you do that, you have a model of the unsafe condition, which is that something tainted touched some sensitive sink. Typically, when you do this, you represent in a dynamic environment. You say, oh, the environment, the files that has been touched by a program, network interaction of the program, shared memory, all this, need to be sort of like given to the system because the system doesn't know effectively what is tainted in the beginning, can reproduce the propagation. And of course, then you have a rule that say that if any value is determined in relation to a value that is tainted, that value is tainted as well. So these are examples that you would find. If A is tainted and A is assigned to B, then B is tainted. Or if B is defined as using A as one of the terms, then B is tainted as well. More interesting, you have control relationship, where you can say if A is tainted and B equal 5, else C equal 8, both B and C are tainted as well, because in a way, their value has been determined as a result of analyzing the value of a condition. And for example, here you can see that you could actually, this is important because this is JavaScript code, malicious JavaScript code, that leaks the content of a document cookie. But since they don't want to, they don't want to send out the document cookie because they control how the data in the cookie is passed between variables, somebody came with the idea of say, oh, if the first letter is A in the cookie, then I'm going to ask for evil.com.a. If the 0 is B, I'm going to ask for B. And this site is under the control of the attacker. So they can just wait and see the sequence of requests that will be made that will completely disclose the cookie. So the cookie has been leaked even though it was never used, for example, to create a URL to be sent out. You can see that you can use just this dependency between the content of something and the actions that are taken to leak the content of the cookie itself. And of course, you have to also represent how you remove taint by sanitizing the content. And this is very critical because, of course, if you don't do that well, or you sort of like mismodel your propagation policy, suddenly you find out that everything is tainted. Because, for example, you cannot model a specific situation where an arbitrary pointer is used to write to memory a tainted value. Now, your whole memory is tainted, and from that on, everything will look like something that is vulnerable. So this is very prone to false positives. And example of things that can, you can model using dynamic taint analysis, a tainted value should never overwrite the return address of the stack, or a function pointer, indexes of arrays. You have seen examples of this when you were developing attacks against the binary data. And also, of course, this works for web application where there is SQL injection or cross-site scripting attacks. And an interesting, and I would say something that has really become super popular in the past few years has been fuzzing, which is a very interesting form of dynamic analysis. The basic idea is that you throw random stuff at a program and you see if it crashes. Yes?
How do you use data for dynamic analysis on peer-to-peer applications?
Ooh.
Is that still like new research? Or like how?
Well, I mean, that's interesting. Let's see. So peer-to-peer applications, so sort of like a content distribution network.
Sure, something like that.
Yeah.
Or maybe like a Facebook-like application, you have a social network and you have people communicating to each other.
Yeah. So this is a very good point. So most of the analysis look at programs in isolation. So you would take one of the clients, for example, and see, oh, okay, I see that the function of this client is to connect to other clients, and for example, get information about the reachability of other elements in the peer-to-peer network. That table could be sent by somebody and could contain malicious values. So there is nothing on a peer-to-peer network that is different.
More challenging in the sense that there's a different problem, but it's more like there's more work to do, like more things to keep track of.
Depends on the type of vulnerability you're looking for. If you're looking, for example, taint-style vulnerability, so I have this information coming in, and suddenly, I don't know, I write to a file based on this, this string that's supposed to be an MD5 of some value, and instead it's a path, and suddenly there is a path injection vulnerability. That becomes, if you want, traditional vulnerability analysis within that context. Then you can use also static and dynamic analysis to, for example, model other properties. For example, you want to understand if, suppose that there are some supernodes, that control a bunch of other, and I'm making this completely up, and you want to make sure that the supernodes only talk to themselves and push down the thing, and there is no way, there is no data flow that allows one of the clients to influence the data that is decided between this superflow. At that point, you would use a combination. You have to take two programs, the client and the supernodes, and have a model of how these guys transfer information among each other, or between the client and the supernodes and among the supernodes, and then have a model that is say, is there a sequence of events that will lead one of the supernodes to store information coming from a client? There will be still static and dynamic analysis. The first case is just normal data flow analysis, knowing that a sink is a path and an open file could be a security-sensitive operation. The other encodes concepts that are specific of peer-to-peer networks.
So very specific based on the application, and then
correct.
The model you're going to make it is probably more complex.
Exactly, and the model, once again, the model of your vulnerability is very important. We have seen, buffer overflows, but imagine that you decide that you want to just do time of check to time of use. That's a different model than buffer overflow. You're looking at possible sequences of operation and how you can demonstrate, oh, okay, this particular sequence operation will never happen. Okay. Okay. So we're going to talk fuzzing because fuzzing has actually received an enormous amount of attention recently because it is a very simple technique in which you provide seemingly random inputs to a program and you try to go for crashes. This works, of course, particularly well with binaries where you provide certain inputs that can cause violation. But there are actually several problems with fuzzy. First of all, how do you provide the inputs? How to generate an input once you have an initial one? How to generate crashes that are actually sort of like relevant, that are actually associated with an exploitable vulnerability, and how to modify the inputs between runs. All these things are, the goal is to have the most efficient process because the process is incredibly repetitive. You have some kind of input generator, that provide the application, which is provided to the application under analysis, which is instrumented by some kind of fuzzing infrastructure. It's very generic, but fundamentally monitors what this is doing. And if there is a crash, it goes in a database, and then somebody's look at this crash and find, oh, I found an actual bug, a 0-day or something like that. The input can be, of course, files, imagine, networks, parameter passed through the command line, and you can have different strategies to take the input and mutate it. You can have randomness, just pure randomness. You can take existing input and mutate it, okay? Or, for example, you can have a grammar that describes what are possible input, and you use that as a basis, to generate input. And of course, nothing prevents you from using a composition of all of that. So the first type of input are completely random inputs, and there is a seminal paper with Barton Miller. They were describing this problem that it was in the 90s, so we're talking about almost 30 years ago, and he was on a terminal line, and it was like the classic dark and stormy night, and so he was on a terminal, and there was some turbulence, some electrical turbulence, and actually, because of that, weird non-ASCII characters will be passed to the command line tools in Unix. So instead of being just ASCII character, will be all these weird characters. And he was noticing that because of this randomness, these tools were crashing. So LS was having segmentation faults because nobody had the idea of passing random crap to LS as a form of testing. And so he did a study in which he took a bunch of completely random data and passed it to all these different Unix utility and find that a ton of them were actually crashing because they were not able to deal with that. So if you do this type of input generation, of course, it's very easy to write. Random stuff, pass it on, see what happens. The problem is that it works only with things that are really, really bad, if you want. And let's say that there is a lot of crash analysis because you have all this crash, but you cannot really easily determine which crash, if they're crashing for the same identical reason or not. And the most important limitation is they will not trigger deep bugs. Usually if you just throw random thing, most programs have some kind of parsing of the inputs, and then they act on the input. And if you have random stuff, the parsing of the input is like gonna look at this and just throw it away. Look at this, just throw it away. And so if you find a bug, maybe is the input parsing, but you don't get to sort of like the deep part. So if you start here, this is your input parsing routine, and this is the actual computation. So there are parts of the code here that will be, used during random fuzzing, but once the data has been parsed, this is where the actual computation happens. For example, there is the rendering of an image. And so with random fuzzing, fundamentally, you stay in that input parsing area of a computation, and you do not reach the other parts, that is where the good stuff is. A different way of approaching the problem is to use mutational fuzzy. And instead of doing this, take an input that, for example, is a valid input. Imagine an image viewer. You take a JPEG that is actually a valid JPEG, and then you ask the system, modify this JPEG, flipping bit, providing some kind of, some kind of positioning of every, bit in the input, and you select a small sample, and then you flip that particular sample, and you push it, and you repeat. So it's super simple, but the idea is that by starting with with a valid input, you will go beyond that initial parsing routine, and you will get to interesting parts of the program. So in this idea, you get much deeper in the parsing routine, and then there is some data that is able to pass by and actually influence the part of the program. The third one is generative fuzzing, which uses grammar. So if you know that the input that the program expects is, for example, SQL queries or things like that, you can actually build a program that generates all sorts of queries and pass it to the program. And those are very good sort of like starting point, at least, for fuzzing. So you know that, for example, your grammar has something that says a string is a value and then the number of character for the value. So a common way of representing string, I put 2 bytes, and I say this is the length of the string, and the data follows. So you know that those 2 bytes express the length, and you can play with that. You can put a higher value and a shorter string, or and for example find vulnerability like Heartbleed or similar. Of course, the disadvantage here is that you have to develop a parser, so you have to do some extra work to generate the right type of code. While with random fuzzing is awesome because you just throw a bunch of trash on the program and you hope it will cause crashing. Yes.
Are there any fuzzing tools that are designed to maximize the code coverage?
Oh yeah, we'll talk about it. We'll talk exactly about that. So of course, you can do sort of like black box input fuzzing, which is fundamentally not look at how the program actually processes all these different mutations, and so you have no idea of exactly that. You might have an idea of the amount of coverage, but you don't know exactly what input are likely to cause more coverage. And you have also some grammar-based fuzzers like pitch fuzz, which, by the way, can also do random and mutational fuzzing that are more focused on the sort of like the type of analysis that requires a grammar. Of course, the right way to do it is, if you can, do gray or white box fuzzing, where you fuzz something, but also you keep track and you look at the internals of a program. That's why it's called white or gray box, in order to understand which of the inputs are actually valuable and which of the inputs can actually be possibly reaching interesting part of the computation. And you can do different type of things, okay? You can, for example, using path constraint, understand, oh, this thing has reached here using this path constraint, so I can change that value so that that particular check will bring me to another part of the program. And of course, you can do this with symbolic execution, and we will see an example that allows you to do more. So in this case, the difference between the black box fuzzing, where it was just input generation, crashes, let's see if there is a 0 day. Here there is this feedback loop where the input is given to the program. But in addition to a crash versus no crash, you get some feedback back, which actually drives your input selection or particular generation. Another problem is the crash database and how you actually triage the different crashes. For example, how you decide you got 2 inputs, you got 2 crashes, even if the different inputs could be the same flaw that's being triggered. And if you have hundreds of thousands of crashes, it's really important to say, okay, give me these 3 because these 3 actually are representative of the same flaw being triggered by a bunch of different inputs. So one way to do it, for example, you record when you get a crash the sequence of functions that are on the stack at that point, and that becomes sort of like your hash. And so if those are always the same, well, you sum them together and you say, well, I don't care about that. I will deal with them all in the same way. And so this is one way of simplifying things. The interesting thing is there are other ways, as we will see in one particular case, for this absolutely super cute bunny, which is called the American Fuzzy Lop. This is the name of the actual type of bunny. But the pun is on fuzzy because this is a very fuzzy bunny, and this is a tool that was developed by Michael Zalewski to sort of bring fuzzers to the next level. And the basic idea behind this was very simple but extremely effective. And the idea is that you take the code of a program, you instrument it so that you record every transition from point A to point B, okay? And the inputs that create new transitions, new path of execution in your programs are sort of elevated and made more better candidates for mutation analysis and the generation of new inputs to the program. And instead of identifying programs using just the stack, the programs are actually identified using branch analysis, which is a better way to identify a program. So in AFL can operate on source code and binary. When you operate on source code, you actually have a sort of a AFL compiler that will add to the source code in specific points certain things that will track and produce a record of all these different transition. Or if you have just a binary, IFL use QEMU in user mode. That means that only the process gets virtualized, which has the nice side effect that since QEMU user mode allows for cross execution, you can actually fuzz an ARM binary on a Linux or a BSD machine. So in AFL, so it starts by having just the program, an input directory with seed input, so initial inputs for the program, and the output directory in which crashes are put. And then simply you run the program, and this is executed many, many times, creating a number of, actually to optimize, instead of being executed from the command line, there is a main program that does sort of like fork exec so that the most of the memory stays in the cache. But the important point of AFL is how branches are recorded. So every time there is sort of a jump to somewhere, you can imagine that the code has some type of pseudocode that as the current location is set to something, some random value determined at compile time. And then there is a chunk of memory that is 64K of memory that is kept there to keep track of all this. It's a big hash table, imagine, that keeps track of all the jumps. And so, for example, you say, hey, I'm going to go to the index in this big hash table that is the XOR between the current location and the previous location, and I'm going to increase the index. So it means I saw one more transition from current location to prev location, okay? And then I send the previous location to the current location, just shift rotate of 1. The shift rotate here is done to fundamentally differentiate between A. So it's just so that if I go back again, either if I go back again or I exchange actually the source and destination, those are two different hashes. If I use just the XOR and I don't do that, since it's XOR, going from this to this or from this to this would hold the same result. And also go to current location to current location would go to the same result than going to other location. So because XORing with itself, of course, would cause 0 to happen. So the shift allows to distinguish between A to B from B to A and A to A from B to B. And the size of the memory is actually an interesting choice because it's big enough to avoid a lot of collision, but small enough that can be held in memory and do stuff fast. So all this is done to collect all the possible branches that happen in the program, and note that this is better than coverage. Why? Look at these two sequences. And these are all basic block of code, so chunks of binary code. And so say first chunk A, then B and C and D and E, and then I have A, B, D, C, E. In terms of coverage, these are identical because they cover the same chunks of code. But the difference is like AFL records the tuple, so A to B, B to C, C to D, D to E. So you say A to B, B to D. Oh, this is a new tuple that I haven't seen before. So good. New tuples are good. Okay? And so even though the same amount of code is executed in different way. So the basic idea is that AFL maintains this map that records all the transitions that have been done and how many times have been done. Because if you remember in the hash table, the A to B are composed to do a hash value, and then you increase this value. So you don't only remember which have been taken, but also how many times. And when a new file introduces tuples that I haven't seen before, that file is promoted as being a better input, something that we should work on because we're just exploring a new part of the program. And inputs that do not generate new transitions then are not necessarily promoted. And it's not completely correct because also there is something that take care of the fact that most of the time interesting stuff is not only that new transition are in, but also how many times. If I have one input that causes a transition to be taken once, and then I have another input, and that transition is taken 5,000 times, that's a pretty good input, and I should keep it, even though it's not just a new transition. So you can see that this is an example. You have an initial one, and you have new transitions like C to A and A to E. And then you can have even longer chains, but there are no new tuples. And so this might not be as interesting. But as I said, we also count how many times a branch is taken. And AFL keeps actually several buckets. The buckets are in ranges 1, 2, 3. You can see that they become more coarse-grained as time goes up, because of course it's different if something switches between 17, or with this other input I just moved to 18. I don't care. But 1 to 2 could be very important, and 1 to 8 is definitely super important. And so this is a way to say if even if you don't have new transition, but you caused a bucket movement, okay, you can see also that this would make a certain input interesting to be analyzed. And so you can see that, if you read the technical documentation, in general, AFL, even by Michael Zaleski himself, is described not as something formal, but as a framework that try to put together a bunch of techniques that are known to work well. And when this happens, you have a bunch of files that are added. Around 10 to 30% are because of new transition, and the rest from increase in the hit count. The fact that a certain transition has been taken many more times for that particular input, and then the input queue is analyzed, and of course, there are the files that cover all the tuples that have been explored, and also are the smallest one, because you have to understand that this is a process, first of all, that is awesome because it can be parallelized very well, because every input can be launched out. But you also want to make it as efficient as possible. So if you have a file that is 15 gigabyte and a file that is 3 megabyte, and they both have the same type of coverage, you know which one you're going to choose. Something that has the smallest possible thing. And so this is how the inputs are prioritized. So you take a tuple that you observe from the set. You find a file that actually covers the tuple that is optimal with little execution. You put that in. You see what other tuples that file has brought in, and you repeat until you have a test set that cover all the tuples that you have seen so far. And at that point, you start mutating that initial group of files to get the best possible set. And there is, there is an obvious approach that prioritize the ones that are very good. So most of the time, if they're not favorite, 99% of the case, they will be skipped. Why not 100%? Because sometimes you want some diversity. You want one every 100. Take something that might not look super optimal, but might open specific direction. And then there are other rules. If the current non-favorite entry was 5, you drop 95% of the time. Or if the current non-favorite entry was not fuzz, then it's skipped 75% of the time. These are just optimization that you use to create something that tries as much as possible to explore the right amount of things. Because, for example, if you start valuing always the same thing, you will always fuzz the same location. And once in a while, you want to look at something completely different that you haven't fuzzed yet. You don't want to get stuck on specific part of the program. And of course, these things can be parameterized, and you can decide, which is the best policy. Then you have the fuzzing strategy. Once you've decided what are the best files, given all the runs that you run so far, you go back, you say, okay, these are the inputs that for me are the best to do what I have achieved so far. Now I want to do a bunch of different mutations. For example, bit flips, you can add or subtract integers from the files. If you recognize that there are specific integers, you can put specific value like 0, 1, -1, the biggest possible value, which are borderline values that are known to cause possibly problem. And also, of course, you can provide dictionaries and do all sorts of splicing and other different type of operations to fuzz the stuff. Yes?
With the tuples, how do you avoid an exponential growth in the number of tuples?
In what sense?
Wouldn't you have if you had 20 different things, wouldn't you have 20 squared tuples or something?
Well, not everything can go to everything, right? So the tuples are just a representation of events in control flow. So it's not that every point in the program can jump to any other point in the program. And so you will observe actually, a small number of tuples with respect to all the ones that can happen with the program, which are not, not even close to be everywhere to everywhere, unless you have a pathological program that can actually do it. Yes?
Why does AFL need to recompile the source code to do that kind of branch tracking? I think you could just apply the patches to the binary.
You could, and in fact, the QEMU stuff does it. But I think that the version that is compiled is more efficient. It's faster. Another point that AFL does is deduplicating crashes. This is because there could be several situations in which, for example, you can have either different bugs that end up being sort of like trigger in some library code, or the fact that using stack traces you could have the same bug that can be reached using different function calls, and therefore two things that appear having two different stack traces are put apart where they're actually the same code. And so AFL uses a different policy, and it makes sure that the crash includes a transition that has been never seen before, and also doesn't have a transition that was in the other crash. And by doing that, it tries to make the crashes, the triages the crash that are more unique in terms of all the others. This is an example of running AFL fuzz. It's very simple. You will have Q, the crashes, the hangs, and you can even print nice plots. This is one that represent the test cases for gzip, and this is 2000 execution, and you can see, different level of test cases in which the input has been repeatedly mutated to find crashes. So one of the limitations of this is that there is no direct support for analyzing network programs. There are ways around it. For example, actually, one ex-student from the SAC lab, now professor at Arizona State, Jan Shishistashvili, has developed a library called Prini that can help using library interposition to make sort of network programs being more like local programs, and so you can run AFL in it. Another example of this type of behavior is another tool called Anger, which we will discuss in more detail next Monday. This is one that has been developed from our lab and has become a very popular tool for analyzing binaries. And this is Anger supports both static and forms of dynamic analysis. It's completely open source. You can get it for free. A lot of companies and researchers use that. The basic idea is that it has several components. There is, a binary loader similar to Radair. You load a program in memory, and you can have information about, the libraries that are mapped in memory, the entry points, and so forth. Then you can have a bunch of static analysis routines that are a lot more than these, and a nice symbolic execution engine which allows you to do symbolic execution, which is a very powerful tool. Yes?
So what about if you're analyzing Java programs, dealing with the Java virtual machine? How does AFL and Anger deal with that?
So very good question. So with the AFL part, fundamentally there is a sort of like a variation of the concept of fuzzing in terms of providing input that have to be, for example, used for a Tomcat or a Java program. So you have to just modify input differently. But then in the virtual machine, you have to change something, and there is where you will track the new transitions. And so you actually look at what inputs created new paths in your Java bytecode. And that's, I mean, to say that it's easy, but it's something that can be
Not too complex.
correct.
So what about a binary analysis?
For the binary analysis, that's a different thing. And so, and Fish knows this very well. So what you have to do, you have to, and this, it becomes a little technical because Anger uses an intermediate language, something called VEX. VEX is, and we will maybe talk about this next Monday, but VEX is sort of the language used by a tool called Valgrind to represent binary code fundamentally. So the basic idea is that you want to do actually all these analyses on binary code, but you don't want to rewrite, the analysis every time for every different architecture. So VEX lift the binary code to this intermediate representation, which has a bunch of advantages. It can really represent all the side effects. For example, when you do in x86 multiplication, the fact that the carry bit or the overflow bit is set is something that is not apparent in that moment in the instruction. Well, instead, VEX make all these side effects, explicit, and so you can reason about it without having to do it. The cool thing is because, they already provided all these lifters. Once you write your analysis on VEX code, you can analyze PPC, x32, x64, x86, x64, ARM. All these things are taken care, but not Java. So with Java, you have to sort of like create above VEX another level of sort of like intermediate language in which you sort of lift the Java code to this intermediate representation, and then you rewrite your technique to analyzing VEX in something that is the common denominator between the two, and now you can use both techniques on the intermediate language for Java and the VEX application. So the basic idea is to analyze Java, which we had to do as you know well. We had to sort of like create a new lifter from Java to another intermediate language and port some of the routines that we use for VEX to that intermediate language so that I work for both. But the cool idea is that now we can do also that for LLVM, for example. That's how we can analyze source code. So there are many things that you can do once you reach that intermediate language. Yes?
What's the symbolic execution?
And that's what is symbolic execution? So this is actually one incredibly cool concept that I think it's very important and has been, it is as we will see at the basis of a lot of automated exploitation. So if you use dynamic analysis and you are executing a program, you're just providing inputs. Hey, here's input A, here's input B, let's see what you do. Well, you might not understand what are the implications of all the possible values that can go there, okay? And you can also have concrete static analysis where only tells you what you can and cannot do, but doesn't tell you really, it doesn't have a lot of explanatory power. So suppose that you have the problem of saying, okay, how do I trigger this particular path condition to get to a specific point in the program? So what you can do is to execute the program in which the values that are passed to the program are not concrete, they're symbolic, they're like variables. So instead of having a specific argv passed to me, I have something that's symbolic. And then, argv is copied in another variable, and in a mechanism similar to tainting, now that variable is symbolic, okay? And as I go through the program, I also remember, and this is the most important thing, the conditions that brought me in that particular state of the program. and what are the conditions on those symbolic values. So at a certain point, then you can sort of concretize. So for example, if I have a set of constraints that I collected with execution, they say a symbolic value needs to be more than 10, it needs to be less than 100, and then I say, concretize it. And there is something I say, oh, 42. It is actually satisfying these conditions, and therefore is a concrete value. Why is this important? Well, if you look at this example, suppose that you have something that is, is an input, and exactly, if x is more than 10 and less than 100, gets to vulnerable code. Otherwise, that's other stuff that we don't care about. We want to get to this. So how do we do it? Well, we use something called a symbolic state. So we start with something that said, OK, I have a variable. I don't know anything about x. It's just symbolic. It comes from, even though in a concrete execution, I would execute the program, pass the value 5, x is 5. But this, I identify the function input as returning a symbolic value. So it's sort of like, imagine it's a lazy evaluation of the actual code. So the cool thing is, like, when I get to that case, if x greater or equal to 10, do this or that, fundamentally, the program decides, I don't know what x is, so my only chance is to actually create two versions on the program. One where x is still symbolic, but I know that it's less than 10 because I took this branch, okay? While another version of the program, x is still symbolic, but I know that x is greater or equal to 10 because I take this branch, okay? So in a way, you split your state in two. And of course, now you have two states, and you have another condition, let's say if x less than 10. So you take this symbolic state, which is the one that is associated with coming to this path, and now you have another two states, one that will lead here if x is greater or equal to 10. And you can see that, this has been added to the condition. So now I have two conditions, and these two will lead me to this, and these two will lead me to this, okay? Now, I have something that not only tracks these symbolic states, or in Anger they're called sim states, but I can also say, oh, and I don't want, vulnerable code. I know that it's vulnerable. When you get there in the execution, let me know, okay? And so once it got there, it stops, and you say, OK, I got to your vulnerable code. What should I do now? Say, oh, concretize. And suddenly, it tells you that the value x will actually drive you here. And this is very powerful because you can see that the semantic insight is enormous. Now, not only I explore the execution of a program, but at a certain point, I can say, hey, tell me how I get there. And this is a very, very powerful thing that is also fueled by, in the case of Anger, of a constrainer called Z3, which is a theorem prover, which is another fundamental tool in security analysis. The basic idea in this case is to have something that you add a bunch of constraint, and then you say, OK, tell me, is there a value that satisfies this? Is this satisfiable or unsatisfiable? And of course, something is satisfiable is there is a value assigned to the variable that are not constants, of course, that make that particular formula true. And is, of course, a formula is valid if it's always satisfiable for any value of the unassigned symbol. And you can check if a formula is valid if you check if the negation is not satisfiable. So this is an example, actually, playing. You can go online and play interactively with Z3. It's kind of a pain because it's functional programming, and not everybody's into functional programming or Lisp-like stuff. But fundamentally, it's something that says, I have a function and I want something that is more than 10 and something that when this function is applied, returns something that is less than 100. And say, oh, can this be satisfied? And also give me a model so there would be a particular set of values that will return and make that particular set of constraints. The cool thing of this is that you can create, there are APIs, so you can actually have a Python program that collects this constraint, set them up in the solver, and then use Z3 to provide answers. And Z3 supports a bunch of types: integer, floating point, bit vectors, enumeration. So it's an incredibly useful thing. So if you think about putting it all together, we saw AFL, we saw Driller. Those are two tools that are incredibly useful to find vulnerabilities, but have different strengths and different weaknesses, which are actually complementary. So AFL is super efficient. You can run it on a ton of inputs, and it's going to find a ton of vulnerabilities, while instead symbolic execution is very targeted. It can find the right value to get in a specific portion of the code, but it is super expensive because every time you have a branch, you're forking a new version of the program. And we're talking about every branch, every jump non-equal in every binary code that would create a new version of the program. And so you can have what is called state explosion, which is usually what makes symbolic execution not scalable. Yeah.
That's what I was going to ask.
Yes. Yeah, that becomes really exponential because every time you have, imagine a branch. Every time you go through a branch, you're splitting your code. Oh, I just did 3 iterations and then I went out. Oh, I did 4 iterations and then I went out. Oh, I did 5 iterations. And every time you split your program in 2. Yes?
Actually, how do the loops sit with anger? How does it?
Well,
I mean, they're just jump conditions over and over again.
yeah, I mean, you can, first of all, you can say, I will follow. So every time you have a conditional, you add a new loop to the set of possible sim states. So imagine, it's like, if this is the state of your program, you have a loop, and suddenly you have 2 programs with some new constraint, and then you have more program. Imagine this like a big, chunk of thing. And at a certain point, say, well, I want to go on from this on. And so this in a way defines like a snapshot of your program. And you can also say, oh no, I want to start from this one. So in a way, every time you decide to do a step, you have to decide which is the sim state that you're going to follow. For example, you can decide, it's up to you for a policy, that if you have a loop, you do every loop only once. Or you do every case up to 3, because then you're already exploding quite a bit. Loops are particularly painful, so there are things you can do. For example, and this we go more in research land, where you identify areas that are particularly difficult to handle, like loops. You decide to sort of jump over, sort of like almost pretend they're not there, until you get to something that is interesting. And if you get to something interesting, then you go back and say, okay, I want to get there because it's interesting. I jumped this difficult part. I sort of like deferred the difficult analysis. And now I will do the right stuff to get at that point, so that you optimize your search of the important parts. Yeah. And so we, for example, decided to look at the composition of AFL and symbolic execution in anger, because we say, hey, fuzzing is cool because it's fast and scalable. Symbolic execution is instead very precise, and it can do things like this, for example. If you have something that checks for a specific magic number, and unless you provide that in your input, you will just stop executing, that's for fuzzing is really bad. You know why? Because fuzzing has to guess that exact number, and until it guesses, every new input is just stopping here, stopping here, stopping here, stopping here, and nothing happens until you get that magic number and it gets here. So these are the classic cases in which symbolic execution, instead it's great, because symbolic execution will just have two states here, one that goes here and one that goes here, and this that goes here, you can say, oh, there is a lot of code after that. How do I get to this point? Oh, your input has to have that magic number, okay? And this was the basic idea behind fuzzing and symbolic execution. So you start, using AFL to constantly do fuzzing like you normally do. And then you wait until you actually get stuck and you don't see a new transition. And then you say, okay, I got stuck. I cannot go in this part of the code. So what if I do symbolic execution up to that code, and then I say, give me a value, set solver, that gives me the opposite of that particular path condition, so that you can start exploring a different branch. So more graphically, imagine that you have something like this, and you start, this is a tool that is called Driller, and of course we wrote a paper on it. But the basic idea is you have something like this, and the initial cheap fuzzing gives you all this stuff. You have X and Y, and you cover all these parts of the program. We call them compartments. But then, you cannot get in the other part, and so you engage the turbo drive, which is the symbolic execution. Super expensive, but super powerful. And it tells you, oh, you need this magic value here to get here. Once you're past, you give the control back to AFL. It goes crazy. It does all these random stuff. So until you're stuck again, and then you call again another symbolic execution, which eventually will cover this particular thing. And we, of course, evaluated this stuff. We used something that I will talk about next Monday about the CGC context that we participated in. But fundamentally, we saw that by using Driller and fuzzing, we could get many more vulnerabilities that we could get without with just using either symbolic execution or just fuzzing. And when I say many more, it doesn't look like many more, because with just fuzzing with FL, we could do 68, and with Driller, we could do 77. But the actually interesting thing is, and I want to show you this graphic, is how deep in the code this vulnerability were. So you would start, this is an exploration where you start from the very beginning of the code, and you can see that the white basic block are the ones that were covered from the initial random exploration. And then the system got stuck and say, okay, let's engage concolic execution. And you got a few other nodes here, and say, we're stuck again. Let's do another invocation of the concolic execution or symbolic execution. And then look, all this other gray stuff were discovered. And you can see how you really have waves in which you use FL to find out about code. Whenever you're stuck, you use symbolic execution to break the barriers and get in other parts of the code and increase your coverage substantially. So, well, this is appearing in NDSS 2016. It's a little, but fundamentally we found a way to combine fuzzing and symbolic execution to sort of take the advantages from both technique and take the disadvantages and complement the disadvantages so that it wouldn't be as bad in terms of scalability. The cool thing is that this has become a technique that has been used fundamentally by every automated vulnerability analysis system that operates on binary. And we'll talk a little bit about our CGC experience, because it's an interesting aspect, especially because it moves from just finding crashes, as we have shown until now, to actually automatically generating an exploit for a certain vulnerabilities. And we'll do that